So much for joining us today. I'm Maureen Gribble with UE Systems, and this is Milan Heninger, and he is here to present the content for us today. We're really excited about his topic. It's not often that we dive into the electrical side of things. We spend a lot of our time talking about bearings and lubrication, but ultrasound for your electrical inspections and your electrical systems is a really great application. So it's time we give it a little shine. So we are still getting used to this new platform that we're using for the webinar. It's kind of cool. We're digging it. It's fun that we get to kind of see each other, and you guys can see the faces behind the voices that you're used to. So bear with us though if we have any little hiccups here or there as we're navigating our way through. A lot of you have already seen that there is that chat, so I like everybody's kind of saying hi to each other, so that's kind of cool. That's the fun part of doing these things live, is we are actually all bringing everybody together here during our lunch hours and whatnot. So continue to interact there. There's also a tab in that chat that's specifically for Q&A. So if you have questions, it's probably best to toggle to that so that I can see those a little more easily without having to scroll through some of the chatter. But we'll do our best to answer questions for you guys today as well. We're going to have a poll question in there, so another opportunity to interact. And again, we just welcome everybody to sit back and take this information in, ask questions, and we'll have a fun little hour here. We are recording this, so if you've got to pop off early, or if you've got a colleague that really would benefit from hearing what Milan has to say, this will be available on our YouTube channel. We can also email the link, so if that's something that you would want, you can indicate that in the chat, and I'll make notes of who to send this to specifically. And again, like I said, we are doing this live, so bear with us if internet goes out or dogs start barking or whatever might happen. We're just gonna roll with it and have some fun. So with that, I'm going to change the screen here and let Milan take it away.
Thanks a lot, Maureen. So yeah, thanks everybody for attending today. I really appreciate it. Ultrasound is a technology I've been using for quite a long time, and I use it a lot in electrical applications, which we'll discuss here in a minute. So I'm looking forward to being able to give you all the opportunity to learn a little bit from me and hopefully get some exposure on new use cases for acoustic and even mechanical ultrasound. So we're going to start off with a little poll, and I think Maureen's running this on the side, so hopefully this pops up on everybody's screen. Curiosity, what are we using ultrasound for in our facilities today? Are we using it for mechanical inspections, things like bearings? Are we using it on lubrication routes for ultrasound-assisted lubrication? Compressed gas and air leak detection, which is kind of a classic use case. And then, of course, we have electrical inspections, all of the above and none of the above. So I kind of expect, based on my conversations with people in industry, to sort of see a bias, especially towards mechanical, but I'm happy to see that right now we almost have matching numbers on the electrical side. But I think there's a good opportunity here nonetheless.
Remember, Milan, it's not none of the above. It's not yet.
That is correct. Not yet.
All right, I'll stop this poll so you can get back to it. But yeah, those good results there. Interesting.
Yeah, this is fantastic. So a little bit about me. As soon as we get the poll down. Perfect. A little bit about me. Again, my name is Milan Heninger. I hold a master's in business administration with some emphasis in renewable energy policy. I'm a mechanical engineer, CMRP, and I've got a variety of other certifications. I've done about 6.5 gigawatts of renewable energy power plants, solar, wind, battery storage, geothermal, about 50-ish facilities in my career. I've done everything from working as a startup and commissioning technician and electrical helper to design engineer to managing facilities and commissioning them. My interests are definitely in reliability, reliability technologies, and reliable organizations. So organizational behavior and reliability, change management, and continuous improvement are all kind of the same thing to me. And it's a very interesting topic for me to figure out how to tie all those things together. And today, I am currently the Senior Manager of Commissioning at Fervo Energy, which is a next generation geothermal company, geothermal power. And one of the things that really interests me about Fervo is that Fervo sees firm, clean power as part of a critical infrastructure network for the United States and the world. I firmly agree with that, and I think it's important that we put all of this into context as how we can look at the industry in power generation, especially in the United States today. So the state of the industry today is one that's being really driven heavily by lead times in our substation and other electrical infrastructure. And so when I was putting this together, I reached out to some of my colleagues and friends and I said, hey, what kind of lead times are we really seeing today? And this is the feedback that I got. So of course, there's some variability. I wasn't picking extreme values. I was kind of picking what we were seeing. But this 50, 60 to 100 week lead time for transformers, be they pad mount or even main power transformers, 50 to 80 weeks on breakers and switches and switchgear. All of these things are putting pressure onto our industry, right? And as we feel this pressure, we have to respond. And the way that we're seeing is there's a surging demand that's driving a lot of this, and it's coming from the data centers, power plants as part of the IRA, so the Inflation Reduction Act, infrastructure upgrades as everyone's trying to electrify and we're getting more and more demand on the grid. And that's adding to also new transmission and distribution. Plus we have some challenges and opportunities with our global supply chain, as well as changes in our trade policies. And the industry response to these things has been a few things. Safe harboring of equipment, increasing their spare parts, looking at using different specifications. So using IEC versus IEEE spec equipment in the United States is something that I have colleagues that talk about. Earlier spend and upsizing. So this is an interesting one. When people are developing new facilities and you're not sure what's available or you're not sure what you're going to build quite yet, sometimes the solution is that you spend earlier in order to lock in prices and availability. But in order to buffer that in your later design phase, you sometimes will upsize your equipment. So now we're buying more and bigger equipment earlier without the full design necessarily being completely done. So these are all kind of industry responses that we're seeing. And what they are is just a form of risk management. Unfortunately, this does create kind of this vicious circle where as the industry is responding, they're increasing demand, which is increasing lead times, which is driving more of this type of behavior. I do believe that this will start to level off, but where we are and where we have been for the last year or so is kind of in this circle. So of course, the question is why ultrasound, right? Why would we feel that ultrasound is useful in managing and mitigating some of these challenges? Well, first and foremost, especially for existing facilities, it allows for early detection of defects. So we will have fewer unplanned failures. If we have fewer unplanned failures, then we don't need to carry as many spare parts. This also has a safety component because we're allowed and able to collect data from distance, which gives us safety. So we can be outside of those arc flash boundaries or limited approach boundaries. And it also allows us to do inspections on closed cabinets. So I put a little note in here that arc resistant gear does present a little bit of a challenge because we may need an inspection port. This really depends on the design of the gear. I have had success on arc resistant gear with ultrasound. It wasn't a big deal, but I've also had some situations where it was sealed up so tight it was quite difficult to get good ultrasound without an additional inspection port. You're going to have to speak with your cabinet suppliers and your engineering teams on that one, but it's just something to keep in mind. One of the reasons that I really like using ultrasound is that it's very fast and easy. I will talk about some of the inspections that I did and how quickly we were able to get those done and get results into the field. But that's one of the main things that I like about it. The other thing that I really like about it is no load inspections. So the last 3 years, I have commissioned or led the commissioning on about 18 facilities, a little over 5 gigawatts. And we started using ultrasound when I took over the commissioning department in my previous role. what we were able to do was find a lot of these defects while we still had construction teams on site, while we were still working punch list, and we were able to work through those things before we actually put real power to the facility. And that was a huge, huge help because loose connections and broken bushings and things like that were getting caught before we were putting real power to the system, just voltage. And finally, we do have multiple applications. As we saw from the poll, there's all of these facility applications of compressed air leaks and bearings and lubrication routes, things of that nature. But on the electrical side, which I'm focusing on today, we have arcing, tracking, corona, and mechanical looseness that are all things that we can easily detect with ultrasound via the partial discharge that they typically create, or in the case of mechanical looseness, some of the rattling and the friction that that's causing. So I want to give everybody kind of an overview of electrical ultrasound and how this works. So in most of your partial discharge, those electrical faults create ionization of the air. That ionization creates turbulence, which is able to be detected by ultrasound. All right, so we're picking this up airborne via the turbulence that's created by ionization. And one of the main forms that we see, especially on your high voltage systems, is going to be corona. So corona is that glow or electrical discharge around conductors when the surrounding air is stressed beyond its ionization point. So it's not flashing over, it's just the molecules in the air are kind of getting torn apart. And that creates ozone, and it can also create nitric oxides. This can lead to corrosion. So we need to make sure that the corona that we're experiencing is something that we can consider, normal, because it can be hard to detect with thermography, and it can be voltage dependent. So at low voltages, we do not expect to see any corona. Anything under 1,000 volts, it really doesn't occur. It may be natural above that 35 kV, which is kind of what I was talking about, is that we're going to see these types of this effect of corona occurring above 35 kV with some regularity. It is dependent on environmental factors such as humidity and things like that. But just keep in mind that it's not necessarily harmful, especially on our high voltage stuff. But it is considered abnormal on anything between 1 kV and 35 kV. All right, so if I go into my medium voltage gear and I hear corona, that's going to start a set of actions to be able to inspect and figure out where it's coming from and be able to mitigate it, because the nitric oxide will cause kind of this white powder on your terminations and cables. That's actually the corrosion and the material getting eaten away from the nitric oxides. So we want to prevent and eliminate the sources of corona, which can often be sharp little points and things like that that are in there. So when we analyze corona, what we're usually hearing is a steady, constant buzzing sound. When we look at the time waveform, we'll see evenly spaced peaks with very little content. Sometimes your negative sequence is a little bit longer, but relatively even peak amplitudes. We do expect to see harmonics that are quite strong at the line frequency. So in the United States, this would be 60 hertz, but if you're abroad, it could be 50 hertz as well. So here's what it typically sounds like. So you can notice that there's just kind of this just real steady buzz. It sounds like you would expect corona to sound. If you've been in some high voltage substations, you should be kind of familiar with hearing this. And yeah, there's the peaks. So tracking. Tracking is the damaging process that's caused by those partial discharges, and it's progressing through a stress dielectric of some insulation. Some people refer to this as like baby arcing, but what we experience here is that it's building in intensity and then it flashes over. It usually requires dirt, contaminants, moisture, or workmanship defects and like stress cones where you cut too deep and don't sand everything off. But you need some path for the electricity to travel along. Usually there's very little or no heat generated. I have seen successful cases where thermography was used to pinpoint where tracking was occurring, but you wouldn't be able to do it with normal camera settings. If you tighten up your range quite a bit, then you can kind of zoom in and be able to see these things. But I would say that on a normal inspection, it's unlikely that you would pick it up on thermography. So when we analyze tracking, we are now getting a more inconsistent buzz with some popping sounds. We get some quasi-random peaks. Lots of content starts to come up between the peaks, and we tend to have a more uneven peak amplitude. You will sometimes have some harmonics show up. Usually what I've seen is that the harmonics decrease as the severity of the tracking increases. All right, so as we move from tracking towards arcing, the harmonic content will continue to diminish. So here's an example of what tracking sounds like. So you get a little bit more popping. It's a little more aggressive. You hear more of that inner peak content that comes in. It just gets noisier. And that's one of those just characteristics. When you've done enough of this, you can listen, you go, that sounds like Corona. And you can listen and go, yeah, that definitely sounds like tracking. But we still are going to go back. We're going to use the software. We're going to do time analysis. We're going to do some spectral analysis to confirm those diagnostic steps. Now, the next form is arcing, where electrical breakdown of the insulation has occurred. We have flashover and there's plasma generation. We have a high current path. We do have heat buildup, and the insulation has failed. The sound tends to be very violent, intermittent bursts. It's aggressive. You get these really abrupt discharges, and you have essentially no content between the discharges, because as it's building up and it flashes over, you get this arc, and then it's building back up and it's flashing over. It can get more and more aggressive to where it does start to sound like a steady, aggressive burning, like you would expect an arc to sound. But because of this effect, we tend not to see anything in the FFT. It just turns into noise. So just a really classic arcing sound. This is one of the nice things about ultrasound. If you've ever experienced these things with your regular ears, you can also pick it up with the device, and it sounds the same due to the way that the signal is being processed into the headphones. Mechanical looseness is kind of the last one, and probably the one that I've seen personally a lot. This is where power connections, fasteners, nameplates are loose for some reason. It could have been improper torquing procedures. It could have been a mistake. There's a variety of things that can lead us there, but ultimately what we are trying to avoid is any risk of arcing, heat buildup, and imminent failure. Okay, so if we have a situation where you have a lot of fasteners, it may or may not be a huge deal. Sometimes we've come across where you've just got one loose bolt on something. I have heard plenty of nameplates rattling. So we have to understand what we're looking at. We have to think about this very holistically as to what the risk is based on what we're hearing and what that specific component is. When we do the analysis on mechanical looseness, we get this rattling, fluttering, non-electrical buzzing sound. We tend to have very evenly spaced peaks that have a triangular shape, usually, and they're always pointing to the right. And what this is the decay. So, whatever's loose gets excited by the line frequency. It starts vibrating and then it damps out. And we're seeing that damp as it points to the right. We will usually show some harmonics, and those harmonics are usually less than 1/2 of the line frequency. This particular signal has lots and lots of harmonics hiding in it, but most of the time it's not this crystal clear, to be perfectly honest with you. But we have to dig in and go look for it. Usually when we're doing mechanical looseness analysis, we go look at the time waveform first, and then we go and we confirm with the FFTs. So an example of what mechanical looseness sounds like is this. So I want you to think about those electrical sounds that we just heard and compare that mentally to this. Notice the frequency is different. It has just a different sound. And that's one of the easy ways to be able to do rapid field diagnostics on this. So I've talked a lot about the analysis side of things because I think it's important to be able to do this when you're doing electrical inspections. But there's a couple of different types of tools that we can use to collect this data. The first one is the acoustic cameras. These can be very useful to kind of locate and classify a variety of forms of partial discharge. And the UE Systems tool is useful for over 200 yards away. It does give you some on-camera and software-based severity assessments for a quick evaluation. So when you're out looking through a substation, you can very quickly figure out where the issues are, and it helps tell you what those severities are looking like. And I find it to be ideal for quick inspections of these large areas where you do have line of sight. Now, there are some limitations there because we need that line of sight, and that to me is one of the big reasons that the ultra probes are quite useful as well. You get more use cases and a little bit more versatility. You can do lubrication routes and things like that with it, but it also allows us to do a lot more precise diagnostics because we have those software tools. In cases where you have competing ultrasound or a more complex situation, I have found that it's easier for me to be able to do the diagnostics using the software tools that are usually used, so Spectralizer in this case, to be able to do these diagnostics. Finally, it does allow for routine electrical inspections on closed cabinets with a lot less risk exposure. By scanning around the gaps of the doors, you're able to pick up ultrasound due to some properties of ultrasound, and it allows you to do some pretty precise diagnostics. And I'm going to give you kind of a how-to here really quick. So let's imagine that this AI rendered version of a transformer is what we're working on. And I want you to see what it looks like with the doors open, because that gives you an idea of what is inside there and where the components are. So when we close the doors, now we still kind of know where these things are, and we're going to use the ultrasound tool in order to inspect around the door seals. As we do that, we're going to start collecting data and paying attention to how it sounds, right? So in this case, I'm going to pretend that we could hear the ultrasound kind of increase as we went up and then started to decrease. Over here, let me switch my pointer so it's easier for you to see. So we start here. As you move up, the ultrasound's increasing, and then it's kind of decreasing in intensity. As we move this way, it's increasing and decreasing. Again, increasing and decreasing, increasing and decreasing. On the other side, we had similar sounds, but the intensity wasn't as high. Okay, so based off of this information, we can kind of triangulate where the issue is. And based off that information, I could be quite confident that we need to go look at these bushings or these T-bodies in order to figure out what that specific issue is. I may bring in other tools. I may bring in thermography. I may go in and do a clean and inspection by shutting everything down. There's things that we can do, but being able to make this kind of more precise diagnostics with the door closed is really helpful in being able to determine not only what the fault is, but then what kind of other tools and technologies we can apply to be able to understand and solve that problem. Now, there are other sources of ultrasound in the electrical world, and we need to be aware of them because they do create competing ultrasounds that can sometimes be difficult to work around, but they can also be opportunities for us to use ultrasound in some other ways. So some quick examples: lighting ballasts, damaged electrical bushings, solar inverters, variable frequency drives, variable speed drives, EV chargers. Those are all creating a lot of ultrasound. I have successfully been able to do diagnostics of inverters using ultrasound. It is way beyond the scope of this webinar, but there is technical capability to do that. A big source of competing ultrasound is ultrasonic rodent deterrents. They are very loud and kind of obnoxious, especially when you're in a motor control center or something like that. Find them and unplug them if you can. If you can't, then figure out a way to shield them, because it will make doing any other ultrasonic inspections quite difficult. And these last three are they do require some special inspection techniques or a unique technical situation, but you can also detect common mode voltage discharge. You can find loose rotor bars inside motors and generators. We successfully did that in a hydroelectric generator at one point. And you can also detect partial discharge inside of transformer tanks. Again, these are a little beyond the scope of this, but these are some other opportunities and sources that you should be aware of. So I'm going to jump into some case studies. So this is real world stuff that I've personally done or been involved with. In this case, this new substation is one that I personally ran the inspection on. And it was a 700 megawatt renewable energy facility located in Texas. This substation is a 34.5 to 345 kV. It has 3 generator step-up units with all their associated breakers and switches. There is one 345 kV breaker and associated switches, and also a capacitor bank in this sub. We did this inspection 24 hours after our first backfeed. All right, so this is very early in the startup and commissioning process. There had been no production loads on the facility whatsoever. And it took me about 90 minutes to go through the entire facility and do the data analysis in the office. So the results of this, I found 48 defects in the facility. I prioritized these as high, medium, and low, and gave the teams some corrective actions that they should do. Clean and inspect, retorques, things of that nature. What we found was that 46 of those 48 were immediately confirmed. They found something that was on the bushings. They found loose connections. They found other issues in that substation and were immediately able to confirm it. What that means is that we had a 96% hit rate, and all of the high and medium risk defects were confirmed and corrected. The two that they were not able to find were some minor tracking that I had picked up. It had a clear harmonic signature to it. We just went ahead and cleaned those bushings anyway, and we didn't really experience too much later on. I've come to find that in pretty much all substations, some tracking is sort of expected. We want to try to minimize that as much as we can. We need to understand what kind of equipment it's on, but those are things that we do see with some regularity. The other important thing is that because this was done during that late stage of the construction and early commissioning, there was really no financial impacts. It was my time and the incremental cost of the tool for us to be able to get all of this stuff taken care of. There was no production outages. There was none of that. So because we caught these 46 defects that were guaranteed at some point to cause a real issue, we just don't know how long necessarily, we were able to eliminate all of those at a time when there was really no major impacts to anybody in terms of finance or schedule, which was pretty awesome. Unfortunately, they're not all like this. I wish all of my stories were this proactive, but there are some that are not. And we had an interconnection failure that occurred at a facility. Now, I'm going to tell you a little bit about the background. At this particular 10 megawatt facility that was part of a 100 megawatt distributed generation project in the upper Midwest, we had a failure. And a high voltage electrical termination failed at our point of interconnection. This was a single point of failure. It was undetected and was an emergency/reactive event. It resulted in a 2-week forced outage. And it was expensive for us to repair this because we had to get people in that could do 12 kV overhead line work on a distribution network. You can see that now we can't shut off the whole line. We don't have lots of other protections. It took us a while to get this fixed. It did result in about $120,000 in lost revenues and $200,000 in total outage cost. Now, this facility was built by the same contractor. We know who did all of the work, and they did all of the work at the rest of the facilities, okay? This presented a real risk to us. So we said, all right, what are we gonna do? So there's a few options. We have ultrasound, we have electrical testing, and we have thermography as our main toolkit for this type of an issue, right? Where we've just had a bad connection that failed. Because the system is online, we really didn't have a lot of options in terms of online electrical testing for this particular design. We also weren't too worried about insulation being an issue. We were really more worried about the tracking, loose connections, and some high temperature connections as well, due to, frankly, some corrosion that was on the fittings that when it was assembled, it wasn't properly cleaned off. So that narrowed us down very rapidly to 2 technologies that we deployed at the rest of the facilities. We went in with ultrasound and thermography. For our thermography, we went in both drone-based as well as with handheld cameras with the appropriate lenses. So you'll see that here. So at one of our first facilities, we did the ultrasound and IR, and we found an issue on this metering cabinet. When we reviewed the ultrasound, we saw that there was mechanical looseness and arcing, which is a pretty severe fault. We went ahead and did a quick thermography. So they shut the equipment down and opened the doors and shot this image. And you can see that there is some pretty extensive heating on this connector, most likely due to a loose bolt. So our technicians intervened. They identified the loose connection and fixed it. But the interesting thing is that they found that that connection was at about 4 foot-pounds when it should have been, according to the design, 40 foot-pounds. Once we corrected that, there was no more overheating, there was no more arcing or mechanical looseness sounds, and that piece of equipment has been in operation since then. It's been almost 10 years. Here's another one at the point of interconnection. There's a drone photo. Again, with ultrasound and IR, we saw that there was an issue at the single point of failure, right? On our POI, we don't have redundant POIs. Our ultrasound waveforms indicated mechanical looseness, and the drone showed that there was some heating occurring right there. Again, likely caused by a loose bolt. Due to the heating, we understood that this is presenting a high risk of failure. We had to get a third party in, but they were able to go in there. They identified the loose connection. They cleaned everything up, put it back together, and solved that problem as well. Here on a recloser at a different facility, we once again did ultrasound and IR, and the ultrasound waveforms again indicated mechanical looseness with arcing. In this case, it was a little unusual. On the T-bodies, on the thermography, you can see that there's some heating that was occurring right where the connection with the wire and the T-body occurs. We knew that there had to be something wrong with this. Our first inclination was maybe it was loose based on what we were seeing, but that was actually not the case. Our technicians went in there, they disassembled the T-body connector, cleaned and inspected everything, and what they found was that it was actually an over-torqued connection. It was over 100 foot-pounds. Once they corrected everything back down to the 55 foot-pounds that was appropriate for that particular T-body, we found that there was no longer any ultrasound being emanating from that, nor was there any overheating. Our fourth facility was again with a line jumper. We did drone-based IR. In this case, there was no ultrasound. So what you see on the left is the image that was as taken, and on the right is after we processed it. And you can see that there is some overheating right there on that, we'll go ahead and call it C phase. But there was, on that jumper, there was some issues. The interesting thing here, and that I want to remind everybody, is that this was actually outside of our project boundary. This was the property of our utility. So we actually reached out to them and explained what we were doing and what we found. And they came out and found that, yes, indeed, there was a high resistance connection. They disassembled it, cleaned everything, and reassembled it according to best practices. And we no longer had an issue on that connection. So in all of this, I've been able to tell you the story of what happened, right? Like what we found as we went from facility to facility in this distributed generation power plant. But what I haven't told you is how do we account for all of this? And we need a way to be able to account for these worst case yet defensible scenarios, which is ultimately your emergency or reactive work. The dumpster fires that we're always trying to avoid as reliability folks. And the way that we do this is through something called avoided cost. All right, so avoided cost is a way for us to define the risk of deferring the maintenance. So if we've detected it, what is our financial risk if we don't fix it soon? And number two, it gives us a cash value to our maintenance and reliability activities. Okay, because once we understand what that failure is going to cost, then we also can understand what it would take to fix it and justify the value of our tools, techniques, technologies, and the people that know how to use it, the training that it takes to be really good at reliability technologies. So the way to break this down is that avoided cost is really simple. It's the assumed cost of inaction minus the cost of your proactive work. Okay. We can go a little deeper on this, and we can look at this as your emergency cost plus unplanned cost minus your planned cost. All right, so this is another way of looking at avoided cost. And I find this to be the most useful because it allows us to break it up into ways that make sense. So on the emergency items, we have our priority delivery. So this is your hot-shotting parts across the country, getting things that you may not have in spare because of all the collateral damage that occurred. This is the overtime, lost production, and additional manpower and labor that is going to be applied to this emergency, all hands on deck type of situation. On the unplanned, we still have a rush on parts, we still have overtime, we still have lost production. And then finally on the planned is our normal parts needs, our standard labor costs, and lost production if there is any. Because when you're able to plan your work, you're able to sometimes do it at times where there is no lost production during a normal shutdown or outage, as opposed to these situations over here on the left where it has forced its issue upon you. And yes, you do see that there are some things that are being repeated, but they're being repeated in a way that we need to recognize that it does cost us more to do emergency work than it does for us to do unplanned work than it does for us to do planned work. And this is just a way to break those buckets up and to be able to show that financial risk as we deal with the issues that we're discovering. So on this project, how did these avoided costs get broke down? First and foremost, you have to understand that based on everything that I showed you, 25% of the plant's generation was threatened due to high risk failures on our electrical systems. So some lead times, at this time, a recloser was a 16-week lead time. Overhead repair work, we knew took about 2 weeks, and that held true for the other repairs that we did. But we also had our inspection times, right? So that the amount of time that it took for us to do that, it was 2 technicians, they worked for 50 hours in 1 week, and they got all of those plants inspected. Our inspection equipment ran about $50,000. That's including the ultrasound, the infrared, and the drones, in order for us to be able to collect all of this data. And then there's some additional manpower with all the analysis and engineering and work orders and things like that. But in this one situation that precipitated from a single failure, our total avoided costs were nearly $1 million. So when people talk about reliability as, oh, it's just, those guys running around with their fancy tools, or, oh, that's not going to fail, or that doesn't, how do you, it's hard for people to understand what we're doing. This is a really tangible way for us to show them that the use of this tool, of ultrasound and thermography in this use case, has saved our company $936,000 in real money, because those failures were going to occur. When you've got bolts that are 10 times looser than they should be, and they're carrying 10 megawatts of power, you're gonna have problems. And honestly, we got lucky that we were able to find all of these issues before catastrophic failure occurred. Now, another thing that I think is important to understand is that there's still an untold story here of a bunch of other savings that we didn't even capture in this analysis. We had a lot fewer safety risks. We were able to manage all of this in a planned way. We had one reactive event, emergency failure, and then the rest of this was handled in a planned and safe way. Because you're doing it in a more safe way, you have a lot less in the rework costs. You're not spending so much time on the emergency all hand deck situations, so you have a lot less in the opportunity cost. You get more, you can use that time for better value activities. We did not take a hit on decreased inherent reliability. Okay, we actually improved the inherent reliability of these facilities. We also didn't skip any of our maintenance work because we were able to build this into our plan. We were able to get it into our regular schedule, and all the rest of the work was still being done. Whereas if you have an emergency, oftentimes your condition monitoring and your other PM work is going to get skipped. So we don't have an increase, we actually have a net decrease in latent defects in the facility. All of these things improve our morale, improved our relationships with our grid operators and our off-takers, and it also had lower administrative costs because we weren't having to do emergency contracts or anything like that. So these are all the other things that we're able to benefit from through just a 1 week proactive activity and taking the steps necessary to eliminate these defects from our facilities. So when we talk about the use of ultrasound in electrical applications, we have to understand that it allows us to have less emergency and reactive work, and that also reduces our collateral damage. Because when these systems fail, it's not just the bolt that fails, they just tend to burn up and cause a lot of collateral damage. So we have fewer unplanned outages, and we have more timely, planned, and safer repairs. We also reduce our risk exposure. Now, risk exposure in this case, I mean it in all three ways. We have physical, technical, and financial risk. It's all being reduced by the use of these technologies in an intelligent way. Ultrasound in this particular case also helps fill some gaps of other remote test techniques and technologies, right? Because we're able to look inside of cabinets that are closed. We're able to quickly check for things like loose bolts that may not show up with other inspection techniques. And it gave us a really rapid return on investment, easy to document our wins for the reliability-based maintenance programs and systems that we were building at this time. And this was a really fantastic case study that we shared extensively internally, and I've been very happy to share it with you today.